Hello, everybody. This is Gigi from Kauai Community College. In this video, we will be talking about alternating series. Okay, so far, we have dealt with series that have positive terms, but many of the interesting series have mixed signs in it, like this one, right? Plus, minus, minus, plus, plus, minus, minus, right? Now, the possibilities of how these signs are mixed up are infinite, right? Because we have an infinite series. And so how many combinations can you make with these signs? Many. All right. But you know what? Unfortunately, we don't have to deal with all of those possibilities. Our focus is going to be on alternating series, which the signs are strictly alternate. Okay. For example, you would have 1 plus 1/2, minus 1/2, plus 1/3, minus 1/4, plus 1/5, minus 1/6. And this is what we call the alternating harmonic series. Okay. So since it has some negative signs, what test will still be okay? Well, the diversion test is still okay to use. Okay. What doesn't work? The integral test doesn't work because it had to do with positive terms. The comparison test doesn't work. The ratio and the root test do not work. So pretty much all the tests we've learned so far do not work, right? Except for the divergence test. So we need to develop new tools. And one of those tools is called the absolute convergence tool. And that will give us a way to use those tests of positive terms with some negative terms kind of series. All right. So alternating series that we already know are these. Okay. Look at them for a second. Yes, they are geometric series. And the first one diverges, the second one converges, right? Now, an alternating series, strictly alternating series, right, where the signs strictly alternate, have the form -1 to the k power times a to the k, or -1 to the k plus 1 power times a to the k. Well, what's the difference? Well, if you're going to start with a negative term or a positive term, that's the big difference there. Okay. And the alternating series test states that if a sub k is positive for all k, and if the condition number 2 is if the sequence of terms are monotonically decreasing, and that the limit as k goes to infinity of a sub k is 0. Now, if those three conditions are met, then the alternating series will converge. Now, the alternating series test does not tell us if the alternating series diverges or not, if it diverges, right? So, well, lucky for us, the divergence test still work. So, again, pay attention to the divergence test before we start the alternating series. Now, why does the alternating series work, conceptually speaking, right? Well, if you have alternate signs, it's kind of go up and down and it creating this oscillating effect. And the oscillation doesn't grow outward because the magnitude of the terms are getting smaller and smaller, right? So as a matter of fact, because the magnitudes go to 0, the upper and the lower portion will come together towards a limit, just like what you see here in this picture. Okay, so that's sort of how that works. And in your note packet, you have a proof of this. So you should go over that just to make sure that you really understand how this actually works mathematically. But conceptually, that's the idea. All right. Now let's consider the series, the alternating series here. And let's verify using the alternating series test. And this is what we call the alternating harmonic series, right? Well, the terms are greater than 0 for all k. The sequence of terms are decreasing because the derivative of 1 over k is negative 1 over k squared, which is always negative. Okay, and the limit of 1 over k is 0. So all three conditions are met. The alternating series test suggests that this alternating harmonic series converges, right? So remember, the harmonic series diverges, but the alternating harmonic series converges. This one, however, doesn't look like an alternating series. But if we write it out, well, for k equal to 1, you have cosine of pi is negative 1. And then cosine of 2 pi is 1. And then cosine of 3 pi is negative 1. So yeah, it is actually alternating between 1 and negative 1. So when we write out the series, it will look like this. We're starting with negative 1, plus 1/2 minus 1/3, and so on. And that can be written as when k equal to 1 to infinity, you have negative 1 to the k power over k. And we've seen this before. We can verify that this alternating series actually converges using the alternating series test. Okay, this looks like an alternating series. It's got negative 1 to the k power. Okay, so let's go and verify. But before we do that, let's just make sure by writing it out, just to get a feel of how it looks like. Okay, and there it is. The terms are greater than 0 for all k. The derivative of k over e to the k power. Well, product rule apply. You will get 1 minus x over e to the x as the derivative. And the bottom there, e to the x is always positive. The numerator is going to be negative only if when x is greater than 1. But since we are considering the infinite series, it is reasonable to consider things that are greater than 1, right? So the derivative is less than 0. So the sequence of terms are decreasing. The limit, well, limit as k goes to infinity of k over e to the k power is the infinity over infinity form. So we can apply L'Hopital rule. So we will have limit of 1 over e to the k power as k goes to infinity, which is 0. So first condition met, second condition is met, and the third condition is met. So the alternating series suggests that this series actually converges. Okay. Now the new tool that we were talking about, the absolute convergence. Okay, definition. If the series of the absolute value of a sub k converges, then we would say that that series converges absolutely. That's the definition. And then if the series of the absolute value of the term diverges, but without the absolute value, it converges, then we say the series converges conditionally. Okay, so those are the definitions. A theorem has been proven that if a series converges at the absolute value converges, then the series actually converges, meaning absolute convergence implies convergence. Now, if you think about the contrapositive of what that said, then we would say, well, if we know that the series diverges, then the absolute value of the series of absolute value would diverge, right? So Absolute convergence imply convergence. And that is a great tool to use for series with some negative terms. Not necessarily the alternating series term, but you could use it for alternating series term. One of the main benefits, though, of absolute convergence is that it let us think about series of non-negative terms, and all the tests that we said didn't work before would apply. All right. So let's take a look at the differences between absolute convergence and conditionally converging. So here's an alternating series. All right. That's how it looks like. We know that's a geometric series and that converges. And then if we take the absolute value of the terms, then we'll get this, 2 over 5 to the k power. R is 2/5, also in the convergence zone. So this series here converges absolutely. All right, here's an alternating series. Terms are greater than 0. The sequence of terms are decreasing. How do we know? If f of x is 1 over ln of x, the derivative would be -1 over ln of x squared multiplied by the inside derivative, which is 1 over x. We know the square part is positive. X is also positive since we're considering all terms from k equal to 3 to infinity. And then the negative there will make that derivative less than 0, and your sequence of terms are decreasing. Now, what about the limit? Well, that's 1 over a really big number, and that is equal to 0. So condition 1, 2, and 3 are met. The alternating series said that this series converges, right? The series of AN converges by the alternating series test. Now let's see if the absolute value of AN converges. The absolute value would be just the series of 1 over ln of k. Okay, taking out the negative terms, just the positive now. Well, that looks like 1 over k. So we're going to use the comparison test. We know that ln of k is always less than k. So when you take the reciprocal, then 1 over ln of k is going to be greater than 1 over k. And since 1 over k, the harmonic series diverges, the bigger series also diverges. So the absolute value of AN series diverges by the comparison test, but we have seen that AN converges. So this series actually converges conditionally. And that's how the definition of absolute convergence and conditionally converges work. Up next is the ratio and the root test. Stay tuned.